think we're almost at 11 o'clock. So a very warm welcome to everybody today to the NIAB Tree Fruit Research Technical webinar. I'm Scott Raffle and I'll be hosting you throughout today's event, which is brought to you by NIAB. I should say at this point, many of you will have recognized me from the past, having presented these events from AHDB. Well, most of you will probably also be aware that AHDB wound down its activities in horticulture last year, and I've now moved to work for NIAB. So we are bringing today's event from NIAB, and you're all very, very welcome.
And hello, everybody. Good morning. So over the next 10 minutes, I want to explain what Growing Kent Medway is to those who haven't heard about it yet or don't understand what it is, who is involved in the program, why you might want to become involved and how you do so. What is Growing Kent Medway? So it's a 5-year program and it's funded by UKRI, which is the UK government's research and innovation agency, through the Strength in Places Fund. It's led by NIABMR, and we are working with 2 university partners in the region, the University of Greenwich Natural Resources Institute and the University of Kent. We are also working with Locating Kent and a number of business stakeholders. The focus of Growing Kent Medway is to boost regional economic growth. And we're doing that through building on existing strengths in the region around technology-driven horticulture, fresh produce packaging, food and drink processing, and its supply chains. And we're doing this through creating a network, and we're hoping this will enhance local collaborations amongst businesses, but also with the research organizations in the region involving research and innovation. So what does GKM offer? So the program will deliver various activities through its lifetime, some of which will be more relevant to your businesses. And I'll expand on those later. But just to give you a sense of the whole program, the program delivers a research and development grant funding opportunities, which I will touch on later, a food accelerator program, which is based at the Midway Food Innovation Centre, part of University of Greenwich NRI. And this will take food and drink businesses, which are at the have early stage products, and it will accelerate them to be market ready towards commercialisation. We have a mentoring program based out of the business school at University of Kent, which will provide mentorship for startups and small to medium-sized enterprises operating in our target sectors. At the centre of it all is a network and events program, which will bring all of these activities to our members. We are investing in new research infrastructure to support the sector through the programme and attracting match funding for that. We are looking into the future for what the 2030 workforce will need to look like. This is involving a skills assessment, which is being conducted to identify the skills our sector will need by 2030. And working with colleges and training providers in the region to ensure appropriate training is delivered to meet those those targets. And then underlying all of GKM's activities is our inclusive growth agenda. So Kent and Medway has some of the widest social inequalities in the UK, and our project works to deliver inclusive economic growth so that all communities in the region can contribute to and benefit from an uplift in regional prosperity, which we're delivering through this investment. So here I just want to give you an idea as a True Fruit audience where some of your challenges and opportunities that you're currently facing overlap with some of the program's central pillars. So one of those is climate smart food production, and carbon is at the center of this. So we are interested in innovations around net zero carbon emissions and sequestration, and it's two areas that you as an industry have as a challenge and opportunity. With waste, we're interested in work that that uses circularity in our sector, and that includes both through the whole supply chain. We're interested in work focused on post-harvest to try and avoid unnecessary waste, and looking at innovations around adding value to byproducts from our industry, and also co-product development. Sustainability is another central pillar of GKM, and this runs through from production through to processing and packaging. And pest and disease and resource use efficiency are just some of the interventions that could lead to improved sustainability in our sector. And then finally, labour. We can address this through innovations in automation, robotics, and artificial intelligence, but also through this Workforce 2030 programme that I have talked about, and delivering skills and education programme. So the new research facilities that Scott has mentioned are also involved in the Growing Kent Medway project. So at NIABMR, we have the Green Tech Hub for Advanced Horticulture. And this is a £11.3 million investment in new facilities at East Malling. The investment has been delivered through UKRI Strength in Places Fund, also the Local Growth Fund from Kent County Council, and a significant investment from the East Malling Trust. And the development includes state-of-the-art research glasshouses, controlled environment facilities, cold storage, some lab space, new lab space. It incorporates a new wine innovation centre, which will become operational in 2023, and includes a horticultural business zone for meetings and events. And here's some design renders that you may have seen, but now this is really coming alive, and the picture in the bottom right is the north elevation of the build, which you will see as you come down the drive towards our main site on the right hand side opposite the concept pair. Our other partners in the project are also investing in new research facilities for our sectors. So at University of Greenwich Midway campus, where NRI is based, they have the Midway Food Innovation Centre. And at University Kent Canterbury campus, they are developing a biotechnology hub for sustainable food and drink. On to the Growing Kent Medway Research and Development grant funding opportunities. So through the Strength in Places Fund, we have a £5 million pot of grant fund that we are investing in industry-driven research and innovation in the horticulture, food and drink sectors over the next 5 years. And this has been split into three strands. So there's large-scale collaborative R&D grants. These are for larger and longer R&D projects, industrial type research, which is industry-led and requires a collaboration with one of the GKM research partners, so RO within the region. We've had the first round, which was launched back in autumn last year, and the successful candidates are just going through due diligence, and the announcement of their projects is imminent. And we have a second round of this competition, which will launch in autumn this year. The small-scale research and innovation grants are more for early stage and feasibility studies. And these I hope to provide a gateway to the facilities I mentioned on the previous slide, and also to foster business-to-business partnerships. And round one of this will be launched this spring. We have a third stream, Technology Demonstrator Fund, which will be launched earlier next year. So we want to, we are supporting business innovation, and my role as Innovation Growth Manager is to help support businesses on this journey. So be it whether you have a business challenge or opportunity that you want developing and wanting addressing, we can work together to identify the right partners, building a consortium, matching you with the right facilities, and identifying the funding opportunities and signposting to resources to help address your business challenge and opportunity. And I believe there's never been a better time to start this innovation journey than now with this Growing Kent and Medway support. Just to touch on some of the NIABMR capabilities that you might want to tap into. So we're going to see a lot of these showcased today alongside those of our GKM partner NRI through the remainder of the sessions. But to give an overview of some of our unique capabilities in crop production, we have expertise in optimizing inputs, be it fertilizer or and irrigation, reduced deficit irrigation and beneficial stresses, how they're applied and the benefits they bring. Incorporation of novel production systems such as vertical farming, and agri-tech development, optimization and demonstration such as sensors, robotics and precision spraying. In the pest and disease and beneficials area, which we'll hear a lot about today, we're world-renowned in developing IPM programs and adapting them to different production systems, and also optimizing control strategies to those IPM programs. Breeding and variety trialing, we have a number of active breeding programs here at NIABMR, covering apple, rootstocks, cherry, and many of the soft fruit crops. And this provides a wealth of germplasm, which has many desirable and novel traits that you may want to tap into as a business. And finally, the demonstration and trialing. We have a number of demonstration sites, such as the wet centre plum, pear, and demonstration vineyards, which provide a useful proving ground for new supporting technologies and processes and help deliver those innovations to industry. We have a changing gears slightly and conscious of time, sorry Scott, we have a new program, pilot program that has been funded through Community Renewal Fund, and it sits alongside Growing Kent and Medway. And I'm just going to play a quick video, hopefully, which you'd have seen in the previous show reel, but this is a free 3-month training program, which is available to eligible businesses. I'm just waiting for the video to catch up, sorry, where you will get a full carbon audit, a tailored decarbonisation action plan, and at the end, a £6,000 grant to put your plan into action. There is some eligibility criteria. You have to be a horticultural or plant-based food and drink business, a micro or small and medium-sized enterprise, and priority will be given to those located in either Thanet, Swale, or Tunbridge and Morling, and your business must be based in Kent. So there are only 40 places on this pilot scheme, so do register today, and my colleague Lauren will put the link in the chat for you to do so. So I've just got my penultimate slide now, which just, I have talked a lot about NIABMR and the Green Tech Hub, given the audience, but just to say how we, NIABMR fits into the bigger Growing Kent and Medway picture. So We are partnering with the other two universities that I mentioned in the region. We're also communicating and incorporating this local civic and business support services and agencies in the region. And beyond that, we have a number of companies that we're already engaging with in this program. And if you would like to join them, join this program, your first point of call should be us, the Innovation Growth Managers. So in addition to myself, based at NIABMR, there's Parag at University of Greenwich and Sophie at the University of Kent. And you can get in contact with us through a number of ways, which I've listed here. And finally, I encourage you to sign up for our free membership, which allows you to keep up to date with our grant schemes, the facility launches, and our events and networking programs. Thank you, and sorry if I went over, Scott.
Thank you very much indeed, Robert. Just to reiterate, robert.saville@niab.com if you'd like to get any more information about Growing Kent Medway. I can also say on the chat, in the chat function, you have a link to the Growing Green for registering your interest. So do please do that. Can I just, one question to you, Robert, because we will have to move on, but I think a lot of people will be thinking to themselves, this is some fantastic opportunity. And what I love about this is the fact that it's industry driven. And so much of the research and research grants have come out in the past from government or other organizations, but I think this is truly industry driven. And can you just confirm this funding from Strength in Places, this ultimately comes from government pot of money, is that correct?
Yes, but in doing so, we also look to industry to co-invest, much like the Innovate UK model. So we're looking for that investment from the industry as well. But yes, that core money is through UK government.
Comes from government, and we all moan a lot of the time about government, don't we? But I just think it's wonderful in today's world that that's coming from them. So thank you so much for enlightening us so well about Growing Kent Midway, and hopefully those of you out there that are listening to this can make more use of it in future. And as I say, please do get in touch with Robert, who can pass you on to his other colleagues in our sister organisations. Robert, thank you so much for now, and we will move on into the main meat of the day, if you want to call it that. We're into our first session proper now, which is post-harvest technology and disease control. Debbie Rees from the University of Greenwich is with us, and she's going to be talking about the latest advances in dynamic controlled atmosphere. In my days, when I used to do a lot of stow monitoring many years ago, I'd never even heard of DCA, and we all controlled our atmosphere by cracking open the air vent and letting a bit of more air in. It's a lot more complicated than that and advanced, and Debbie's going to tell us a little bit more about it. Good morning, Debbie.
Good morning. Hopefully you can hear me. I'm sure someone will tell me if you cannot.
We can see you and hear you perfectly, so that's wonderful.
That's an advance. Okay, then I'll start. So my name's Debbie Rees. I work at the Produce Quality Centre, the PQC, led by the University of Greenwich, but based at East Malling, and actually right next door to the beautiful Green Hub. Proud to be part of Growing Kent Medway. So today I'm going to talk about dynamic controlled atmosphere, or DCA, which is used to monitor the state of apples during long-term CA storage, and specifically to detect low oxygen stress. So the objective of this talk, my objective, is to explain the technologies to help storers make informed decisions. My colleagues and I at the PQC have worked on a number of these technologies for a number of years. I will admit I'm a bit of a nerd, so there will be some nerd points put into this talk, which you can ignore if you wish. Okay, so first of all, why do we want to use low oxygen storage? It can extend storage time. It can also reduce specific storage disorders. And in fact, one that was very notable was surface scald of Bramley, which used to be controlled by DPA, but when that was no longer allowed, low oxygen storage gave a means of actually controlling this. Low oxygen can also control Brayburn-Browning disorder. However, if we take the oxygen concentration too low, we can also have problems. And in this slide, you can see that for Bramley, whereas low oxygen is indeed controlling scald, if we take the oxygen too low, we get softening. We also get alcoholic taints. So we want some way of detecting what is the lowest oxygen that we can use. I'm going to focus on two types of DCA technology today, using respiratory characteristics and looking at chlorophyll fluorescence. I'm going to start with respiratory characteristics. So changing the atmospheric composition is the basis of controlled atmosphere storage. As we take the oxygen down from the air levels of 21%, there comes a point where we reduce the rate of respiration and therefore we slow down metabolism. We can measure that rate of metabolism by the rate of respiration, which we can measure in two ways, either by the reduction in oxygen levels or by the evolution of CO2. And both of those are shown in this graph. You can see both of them dropping below about 2% oxygen. However, there comes a point where the fruit goes anaerobic. And at that point, we see that the CO2 evolution rises as the fruit starts to ferment. So this is, we call this the low oxygen level, and below that, we obviously don't want to store the fruit because it starts going alcoholic. So we can detect that point by looking at the ratio of the CO2 evolution to the oxygen consumption, which we call the respiratory quotient. And it's shown by the red line here. And you see that when it gets down to a certain level, at the point where the CO2 is rising, we get a very distinct rise in this RQ. We do also see evolution of ethanol, but I'm not going to talk about that today. Okay, so the first technology that I'm going to talk about is the Safepod technology that was developed by SCS Limited. This consists of a respiration chamber into which about 75 kilograms of fruit is placed. These chambers can be put into commercial storage. The picture at the bottom here shows an American store, and the picture on the right shows a UK store with the Safepod chamber placed at the top of a pile of pallets. So to explain how this works, here the Safepod is placed within the commercial store, and most of the time it has valves in the base which are open so that the fruit in the chamber is experiencing an atmosphere the same as the store. So it's basically shared with the store. Periodically, we can close those valves. And at that point, the atmosphere in the chamber is affected by the respiration. So we see the oxygen decreasing as shown in that blue line and the CO2 increasing as shown in that orange line. So we can use the slope of those graphs to measure the rates of respiration. And the graph at the top here shows you both the respiration as measured by oxygen consumption, that lower line, decreasing as the oxygen concentration decreases. You can also see that the respiration as measured differently by the CO2 evolution decreases. But as I said before, there's a point at which it starts to increase. This is the at the anaerobic compensation point, or ACP. So we can use those two, the ratio of those two rates, to measure, to calculate the respiratory quotient. And that's shown in the bottom slide here, bottom graph here. And at one point, the that RQ starts to rise. The lowest point there we call the lowest oxygen level, and this is the critical point for storage. Okay, so I should say nerd point here that basically if we measure these characteristics rapidly, and practically we want to do that over just a few hours, we have found that we shift that graph so that the lowest oxygen level is actually shifted up a bit. We know that, we take that into account. Okay, so an alternative is not to use a chamber, but to measure the respiration rate, for the whole store. And this is the basis of the dynamic controlled atmosphere method called Fruit Atmo, which is sold by Frigotech and in this country by JD Cooling. However, it is more accurate to measure that respiration using the carbon dioxide evolution than the oxygen consumption, basically because the oxygen leakage from the store can be significant. So for this method of DCA, we just measure the carbon dioxide respiration. In fact, the way that the company shows it is usually in a graph like this. So several measurements of respiration rate and using a curve fit to find the oxygen point at which that respiration is a minimum, and that is the anaerobic compensation point. So to summarize, as explained by the company, the CO2 evolution rate decreases as the oxygen concentration decreases until the anaerobic compensation point is reached. Below that, the respiration rate increases as measured by CO2 evolution. So this is used to measure that optimum oxygen concentration. Okay, whistle-stop tour. Now we're moving on to the second type of technology, which is the chlorophyll fluorescence. So in the skin of the apple, there are chloroplasts, and these chloroplasts can photosynthesize just as chloroplasts in leaves can. So in photosynthesis, light is absorbed, it's used to make sugars. No process is ever 100% efficient, so that some of the light that is absorbed cannot be used for photosynthesis and is re-emitted as fluorescence and heat. So we can look at that fluorescence. Basically, if the chloroplasts are unhappy, they become even less efficient and the fluorescence rises. And that is what we use as the basis of this technology. Now, nerd point here, it amazes me that apples, even stored in the dark for months, even up to a year, are still able to photosynthesize. It's important for this particular technology, but I have to say, as a biologist, that just blows my mind. Right, so one of the technologies which uses this phenomenon is the Isocell Harvest Watch. And this slide here shows one of the chambers or kennels of the Harvest Watch placed, or here 6 of them actually, in a pallet bin. So this has both the excitation light and the sensor to be able to measure the level of chlorophyll fluorescence coming from those apples. In this screen, you see the data which is obtained by the Harvest Watch system. So the oxygen concentration is being decreased in the store. The chlorophyll fluorescence, at the point where the chloroplasts are unhappy and start screaming, suddenly shoots up, in this case at 0.1% oxygen. So one of the questions is, how is it that the chlorophyll fluorescence at the surface of an apple can actually respond to what's the damage at the heart of the apple? I don't know fully, but I know that we've tested it. Scientists at the PQC have done a number of studies, and it is indeed true. And the response of chlorophyll fluorescence is actually very similar to the RQ response that we see in the other technologies. There is another technology which is being marketed at the moment, the Fruit Observer, which also works using chlorophyll fluorescence. And on this slide, you can see that the oxygen is being dropped and there's an increase in the fluorescence level. Okay, so finally, things to think about. So when you're using these technologies, it is better not to mix fruit consignments in stores. If you are using a technology to detect stress, then obviously you want to be able to detect the stress for the types of consignment that you're looking at. What is the safe margin above that level of oxygen that we've detected as the critical level for storage? And generally our answer is that we use 0.2% oxygen above that detected critical point. Another point is that during storage, apples slow down their respiration rate, and it's generally been observed they become less sensitive to low oxygen. So should we reduce oxygen concentrations later in storage? For the final technology that I showed you, this is data that has been obtained by Fruit Atmo, showing how the critical oxygen decreases over time. So the question is, should one reduce the oxygen levels? In practice, I'm not seeing that happening in commercial stores, but it's a point of discussion. Is it ever right to take the oxygen lower than that critical point that is being measured by these various technologies? There are studies being done critically in Brazil and the US, where scientists have tried deliberately storing apples below at a level where they will be producing ethanol. I have to say I'm skeptical. I don't actually believe that that is something that should or will be done commercially, but again, a point of discussion. So final thoughts. All those technologies that I've shown today, all of which I think are good ones, one of the things that they do is monitor the response of fruit to storage, providing data on that behavior. This provides an opportunity for data gathering to feed into improved predictive modeling for storage potential. I guess this is a call to the industry to work together to improve storage in the future. Okay, thank you very much for listening to me. Please come and talk to us at some point. Thank you.
Thank you, Debbie. Just hold on a second. Thank you, first of all, for such a clear and concise presentation. It was very helpful. And it's amazing how the technology has moved on. I have got one quick question for you. This question says, if you have oxygen leakage, it will be very hard to maintain DCA levels unless you use a lot of, sorry, beg your pardon, I'm dealing with another answer to that. The question was, is there too much oxygen leakage in the room? If there is too much oxygen leakage into the room, how are you meant to keep low oxygen for the storage period? Don't know if you can answer that one.
I would say with difficulty. I think that effective DCA does require high spec stores. So I think that would be difficult.
Yeah, the response in the chat room here is if you have oxygen leakage, it'll be very hard to maintain DCA levels unless you use a lot of nitrogen. Best not to have any leaks, that's the answer.
Exactly.
So, Debbie, we must move on. Thank you so much for sharing your extensive knowledge of that subject. And we will move on to your colleague, Richard Colgan, who also works at the Storage Technology Centre at Greenwich NRI. Now, Richard is going to talk about rots, storage rots and storage disorders. Now, the interesting thing about this is that in the good old days, we have always had to chop fruit and look inside to see what's going on, looking for things like low temperature breakdown, core flush, and so on. I understand that Richard's going to tell us about some new technology which may find new ways of assessing fruit for disorders and diseases. Good morning, Richard.
Good morning all. Thank you, Scott. So this is a bit of a run through of different technologies that we've been testing out with other collaborators over the last 4 or 5 years. So these are not actually ready yet for commercialization, but they will hopefully have some commercial impact in the near future. Okay, so I've got to talk about 4 different technologies here. So the first one is done by some colleagues of mine at the University of Greenwich. Direct analysis of the skin surface of the fruit.
Richard, can I interrupt? We have got a problem with the line. I don't know if you're able. We were getting a little bit of. We were getting a bit of interference, and now you've gone very, very quiet.
Can you hear me now?
Not at all well, I'm afraid. Have you got a headset?
I am wearing one actually. Yeah.
Wearing a headset. Okay. Maybe the connection is faulty.
Can you hear me now?
It's not well. Do you want to try taking your headset out?
Can you hear me now? Unfortunately, there's a bit of background noise. Is that all right?
That is better than it was. So perhaps if we proceed on that basis, let's use that system.
So the technology I'm using, I hope you can hear me, is technologies that we've been testing at the University of Greenwich and partner organisations, University of Kent and University of Manchester, and also NIABMR. So looking at 4 different areas of work that we've been doing. These are not technology ready, but they're certainly in the next 5-10 years, they might have commercialisation potential. So the first area we're going to talk about is direct metabolite screening of pathogens. Then we're going to look at volatile detection for diseases, particularly neonectria. And then a couple of technologies that we've been using to measure fruit quality, so looking at skin surfaces and internal quality parameters. So before I start, I mean, there are different technologies out there for measuring gas metabolites. Traditionally, we use things like gas chromatographs, which are expensive, but are very accurate and can measure many different volatiles at the same time. Then you have things like in the middle here, electrochemical sensors, which we often use, say, in storage for oxygen CO2 analysis. They are relatively cheap, but do require power to run them. And then we have the new technologies, it's called thin film sensors. So these are sort of technologies that you have on your mobile phone that when you put your finger on a phone and scroll up and down, it's very similar technology to that. And potentially they're quite cheap to generate and can be applied across multiple sensors in a store. So I'm going to talk about both ends of these technologies, gas chromatograph analysis and thin film gas sensors. So this is work with my colleague, Dr. Ian Goodall at the University of Greenwich, using what's called a DART machine. This is a high value laser, helium laser, that you can put samples directly underneath this laser and it will measure the surface chemistry. So it was designed in the pharmaceutical industry for measuring counterfeit drugs. In front of this laser, and it will tell you if it's a kosher pill or not. We've been using it in more applied areas, looking at surface of fruit, particularly apples, also blueberries, to try and see what the difference is in skin quality over time. But in this talk, I'm going to talk more about disease, trying to detect diseases, and in particular, we've been quite keen to detect neonectria, both on the fruit surface, but all equally as we use for looking at the trees, detecting nectar lesions, canker lesions on trees in the nursery. So the outputs of this, when you put bits of surface tissue in front, you get different spectra. I'm not going to worry about the spectra, but on the left hand, top hand side, you have a healthy apple with lots of volatiles associated with esters and volatiles of flavour. You have infected disease tissue down the right hand, bottom right, you get a lot less volatiles, but different profile of volatiles. Some are associated with infection and disease. So what we can do with that information is to put it in present it in a much clearer way to start doing some data analysis and separation, present it in a more sort of digestible manner. And this way we can show that using tissue samples directly put into the
Richard, sorry to interrupt. The sound quality is getting really poor.
Oh,
I think a lot of people are really struggling to hear you at the moment. One option that we do have is to just stop and see if we can get your sound quality sorted.
yeah, should I stop and restart later on? I might get these headphones somewhere. Yeah.
I think our audience would largely probably be in favour of that.
Right. Okay.
We might just have to move on to our next speaker, but if you're able to find another headset, we do have a problem with it.
Right. Okay. Sorry. Yes.
No, sorry, we're having to stop you there. So if you stop presenting, that's fine. We'll have to now move on, and hopefully we can get Richard back a little bit later on to finish that off, because I know a lot of people would have wanted to hear Richard's presentation and talk. So we will move on. Our next speaker is Chris Cook, and we're moving into disease now, disease topics. Chris Cook is a CTP student. That stands for Collaborative Technology Partnership. And he is based at East Malling, NIAB at East Malling. And he is looking at something that has been a major problem for apple growers for very many years now, apple replant disease. And all sorts of technology have been looked at to try and resolve this problem, and we've never really found a complete solution. But Chris is trying to understand the resilience of the beneficials in the soil to see whether we can combat apple replant disease. So Chris, tell us a little bit about your PhD study and how it's progressing.
Thank you very much, Scott. Hopefully everyone can hear me and see my slides okay, and I will crack straight on. So my overall project is looking at soil microbiome and understanding how that interacts with the tree and in terms how that causes replant disease. So I've only got a short amount of time today, so I'm just going to go over one trial that I've been conducting and a bit of background on replant and where we're at the moment. So when we talk about replant disease, what are we talking about? Well, it's defined as the planting of successive generations of apple trees without any rotation or land rest between those generations of crops. It's generally caused by pathogen complexes, mainly oomycetes and fungal pathogens, and it's exacerbated by nematodes, which cause lesions in the roots and allow for wounds to develop and the pathogens to invade the root system. It's genuinely a worse disease in dessert orchards than it is in cider orchards. That tends to be because the amount of replant and rotation that they do is a higher volume in a dessert orchard than it is in a cider orchard, and they have a more in-depth focus on fruit quality in dessert orchards as well, which is one of the symptoms of replant disease. So when I talk about symptoms, there's kind of the above ground symptoms that you can see on the right and the below ground symptoms that you can see. So above ground, we see stunted growth of the tree, a reduction in the overall vigor of the tree, and a reduction in the yields and the fruit quality of the tree as the vigor is reduced. And below ground, we can see root tip necrosis of the roots and a general reduction and size in the root system and the root health. So how do we treat replant disease at the moment? Well, the standard treatment for the last sort of decades has been chemical fumigation. But this has always been an expensive process, and there's increased pressure from government legislation that has caused a lot of banning of the most effective chemicals that we had before. And any chemicals that we genuinely have left are not as effective as the ones that we had previously, so they're becoming less cost effective to treat replant. There's anaerobic soil disinfestation, which is the process of applying a product to your soils and then covering the ground with some sort of plastic. And this creates anaerobic conditions. And then in turn, what they think happens is a greater number of bacteria develop in the microbiome, and this controls the soil-borne diseases through that increase in bacteria. Soil biofumigation is a tactic that lots of people were looking at to try and use biological products to achieve a similar effect to what we were seeing with the chemicals. So something like brassica seed meal that's been highly studied in the USA is one such product, but this only has an antifungal and anti-nematode action, and it is not effective against the oomycetes. So you still may see things like Phytophthora infection and disease through when you apply things like brassica seed meal. So it's not an overall control. And an alternative strategy, which is more my interest, is can we apply a beneficial product to the soils to increase the overall health and nutrient exchange with the root system to increase that vigor of the tree at time of planting. So products like this include arbuscular mycorrhizal fungi, which work symbiotically with the root to exchange nutrients and in turn adds a benefit to the tree. Biocontrol agents, so whether we can add a product that will treat the pathogens that are in the soil and through niche exclusion or just through other functions of the biocontrol, or plant growth promoting rhizobacteria, which is obviously the bacterial version of arbuscular mycorrhizal fungi, so something that will have a benefit towards the root and to the bacteria itself. And hopefully these will have long-term action if we apply them at time of planting, and that's something that I tend to be looking at in my research. So cultural practices is also a major factor in replant disease. So one such measure is planting position. So what we want to do is try and avoid the tree station where they were previously planted. So we could do that by planting in alleyways, but this is a very expensive process for a lot of growers. They may have things like pre-existing irrigation lines, or they may have sort of compaction or something in the alleyway, which means it's not feasible for them to move their trees into the alleyway. So chances are they will replant back in the same tree station. Virgin land would be the sort of golden bullet to treat replant disease, but there's not a lot of that around. And we're talking about the most expensive one, moving your entire orchard to a different site that's never had a crop on it would be the most expensive method. Adding a break or a cover crop. So planting something like brassicas in your field for a season or maybe longer to give the soil a break and to sort of adjust the dynamics of your soil underneath would be a good measure. But if a lot of growers, if they haven't got apples in the ground, they're not making money. So something like switching to brassicas is going to have to acquire different machinery, for example, that they may not have access to. And also they want to have their apples in the ground for a long period of time. Good hygiene. So when we remove apple trees that were previously there, try and remove as much material as possible. But if you're using mechanical measures to remove trees, this is almost impossible to try and get all of the previous root system out of the ground, and they're so prolific in the way that they function under the ground that it'd be hard to get all the root system out anyway. And one measure is sort of the selection of the rootstock that we use. So trying to select a rootstock that has high tolerance to replant disease, and sort of the genetic relationship of the rootstock to that was previously planted is one measure that we've been looking into recently and what I'm generally going to talk about today. So a trial I want to speak to you about was a 5-year-long trial that's been going on as part of the UKRI Horticulture and Potato Initiative. We went to a Heineken orchard in Worcester to do this trial, and we planted 7 different rootstock genotypes of the most important rootstocks in the industry, and we grafted them onto Worcester pear main, which we chose because it can be used as a cider and a dessert apple. So it was a good variety to sort of cover both of those industries. And we planted the tree in the previous tree station on the right-hand side here, and the corresponding alleyway in between. So the trees were only around 1 meter separated in terms of their planting position. So in the orchard, before it was grubbed, it was previously MM106 and MM111 rootstock grafted to Katie. And what we theorized here is that if we saw an increased establishment in the alleyway compared to the corresponding tree in the tree station, then we're seeing replant effect on the tree station. And we can theorize that planting an alleyway is an effective way of treating replant. So this was the girth measurement. So what we did is we took the value of the girth measurement in the alleyway and we subtracted the value of the girth measurement from the tree station. So if we saw that that value was positive, so the girth was larger in the alleyway than it was in the tree station, then we could say that there was a more severe replant effect going on in that rootstock. And equally, if it was at 0, so there was no difference between girth, or actually if the tree station had a higher girth than the alleyway, then we could say that there was no ARD or a reduction in ARD, almost a reverse effect. And then what we did, we just took the sort of change in time over this. So obviously, if the value becomes more positive, then the tree is larger than it is over time. It's getting larger than it is in the tree station. And then we could see that anything we had above 0 had a replant effect here. And what we saw is 5 out of the 7 rootstocks that we trialed were showing some sort of replant. And the most severely affected out of the 7 that we trialed were 116, 106, and M200, which was a morning breeding rootstock from the breeding program. So we assigned a score to each of these. So the most severe had a score of 2, the intermediate had a score of 1, and anything that had no replant had a score of 0. And what was interesting about this is when we look at sort of how vigorous the rootstocks were compared to how tolerant they've been reported in the literature, 116 and 106 tend to be at the top sort of end of that. They should be the most vigorous and the most tolerant to replant. But what we see is we had 116 and 106 that were most affected. 106 itself was previously there, and 116 that we were seeing a replant effect in had parentage of 106. So what we identified is that there's a genetic link here between the newly planted tree and the previous generation of tree that's planted, and that leads to a more severe replant effect, more than what we would see with just looking at the reported response to replant through whether it's susceptible or tolerant. It might actually be that the genetic link is more important than that. And when we look at what diversity we have in our soil, so this is looking at the bacteria between the alleyway and the tree station. So we've got obviously a lot of data here. So this is a non-metric multi-dimensional scaling plot. So it's just a way of visualizing a lot of data in 2D space. So what you want to see is clustering. So if 2 points are in the exact same spot, they have an identical bacteria population under them. So you want to see clustering away. So for example, we see here there's very distinct populations between alleyway and tree station on this trial for bacteria. So even though they're only 1 meter apart in terms of their planting position, they have very different bacteria microbiomes here. And similarly for fungi, we saw the same effect. It might be a case that we have a very different microbiome. But what's more interesting, and what I was quite interested in, is what was the difference? So in those most severely affected replant disease trees, so if we go with the score of 2 here, which was the 116, 106 and M200, what was the difference between alleyway and tree station? Or were they different, or were they identical? And what we can see is roughly, with how I've circled them, but they're quite different. And that would, for bacteria, we see there's quite a big difference here. And the next step for this trial would be to identify what these differences are. And when we look at fungi as well, because obviously fungi are the main cause of pathogens rather than bacteria, there's some differences again, maybe less pronounced than there was in the bacteria, but we are seeing some distinct different population. So sadly, this is the sort of end point of this work at the moment, and sort of my next step with analysis will be to identify what these differences are, because that's sort of the key word that probably everyone's shouting with their questions, is what are these differences then? Are they pathogens, or is it just differences due to, like I said, compaction, or the fact that the tree station has had things like fungicides applied for the whole time that things have been planted there? Is that the main difference, or is it something more? So some summary points to sort of bring all this together. Chemical fumigation is no longer viable, I think, because of the cost effect and how effective it's become. Ineffective it's become, I should say. And virgin land is obviously an impossible strategy and unrealistic. What we should do is genetically related rootstocks suffer more from replant disease than what we've seen on this trial. So if you can plant something that's genetically different to what was there previously, you'll probably see an improvement in the establishment of your tree in the early years. Rootstock selection and planting position are going to be difficult. We understand that economically it's going to be hard for a grower to move his crop over to the alleyway, but if you could do it, if you could sort of isolate maybe one section of your plot and trial it out and see whether you get a benefit, maybe it might be financially beneficial in the future. So it'd be a good discussion point for any grower who's looking to overcome replant if they have it in their orchards. And future research should focus on this link between genetic tolerance and soil treatment. So if you could select a rootstock that's genetically different and apply a beneficial product to it that increases the establishment of the tree, that might be the best way to sort of have a integrated package of management to overcome replant in the future. And that would probably be where research in the future would go, moving on from this research, from my work. So I just want to say thank you to obviously my supervisors at Cranfield and NIAB and everyone who's been involved with this project. And I'm happy to take any questions that I'm sure you have on my work. So thank you very much.
Thank you so much, Chris. That's excellent. I think it's, I've always been of the view that the answers to these problems lie in genetics and the genetic manipulation of rootstock material. And I'm sure there will be an answer at some point. There is just a comment I'd like to bring out rather than a question. Nigel Kitney, who used to be the AHDB Tree Fruit Panel Chair, is just pointing out that a similar effect was found with 106 and 115 in the AHDB canker rootstock trial. G11 and G41 gave the best growth. So I just wanted to point that out to people who hadn't seen that chat. And final question really to you, Chris, is how much longer does your study continue for? At what point are you into your PhD studies?
So yeah, so I'm in my final year now. I finish in September. So I'm sort of wrapping up things now and hoping to publish some of my research that I found over those years. So hopefully there'll be some peer-reviewed stuff out soon on what I found.
Well,
yeah, right at the end.
Thank you. Oh, that's great. And thank you for sharing your information with us so enthusiastically. And we wish you well wherever your next role appears. So thank you so much indeed, Chris. Now,
thank you.
The good news is, folks, that we have Richard Colgan back. We have him set up with a new microphone and ready to go. So I'm going to propose that, Richard, can you hear me?
I can.
You can? Oh, that sounds so much better.
Sorry, yep.
If you want to carry on from where you left off, and we'll move on with that. Okay.
Yeah, I apologise, my hard drive was whizzing around. So yes, so the work we did with this DART system, we actually managed to detect different pathogens in the fruit surface by putting tissue samples directly in front of this laser. But also we could actually take swabs. So we actually take some swabs of the surface of apples infected with various diseases, and then got the same sort of results, discrimination. So I think it's a very powerful technique, but obviously a lab-based technique. But some of those volatiles that we picked up on, we actually tested to see what they were doing in terms of, some of them were related to the pathogens, some related to the host plant defense system. So looking at where the disease was spreading into the tissue, we took some samples and measured some volatiles. And we came up with a couple of essential oils, which were present in the apple, but were very effective at controlling the neonectra growth in culture. So these are two essential oils, which we found to be equally as effective and potentially maybe a new treatment in the future. So that was some rather high-end level areas of detecting volatiles. So we also involved in an Innovate project looking at advanced and low-cost sensors. This is involved with NIABMR, University of Manchester, and a company called Cambridge Display Technology. And this was looking at trying to produce some very low polymers, low-cost polymers, which we could detect volatiles that were associated with disease. So in this case, we were also detecting volatiles from apples, the headspace of apples, both apples in jars, gala apples, but also some disease like neonectra in culture. And then looking at the signature profiles of those volatiles in a GC. And then using those volatiles to train sensors to detect diseases in stored apples. So these sensors are very thin polymers. They're called they're similar sensors you get on your mobile phone. They're a polymer made up of several layers of different printed electronics. They're supposed to be very low cost. So they can be deployed multiply across the store potentially, but also have their own power, so they can actually use wireless connections to detect, to communicate with those sensors. They're very small, they're the size of a 20p piece. They're quite flexible, they're called OTF sensors. There's quite a lot of technology involved in generating them, but they have great potential in horticulture and agriculture. So with this technology, we were training the different sensors to detect different volatiles in the headspace of stored fruit. And we found a couple of sensors that are really good at detecting some of the signature volatiles associated with neonectra infection. So this potentially is a new way forward of trying to detect diseases in store. And they will quite happily discriminate between the healthy apples and those that have neonectra. So for the future, this is quite a good technology. So another technology I want to talk about today is the use of non-destructive technology to look at internal quality of apple. This is called bioimpedance spectroscopy. It's an electrical inductance magnet that we can put apples through, and it can start to look at the internal quality, both in terms of bruising, tissue breakdown, rots, and also ripening. So potentially looking at things like firmness. This is done with University of Manchester. It's been used in the past looking at things like potato bruising. So we've now been trying to look at it to detect internal, in this case, core flush in apple. So basically the principle is that you can put electric current through tissue, and it acts like a capacitor. And as the tissue changes in its integrity, then the electrical inductance changes. So as cells become more senescent and leaky, then the electrical current coming through those cells, passing through those cells, will change. And you can pick up that difference in the electrical waves coming through the system. So this was a prototype that was produced by the University of Manchester in an EU project, where they had fruits going through a mini conveyor belt with the magnets and the electrical inductance happening inside this big magnet. So what they've been able to do in a similar project that we're working on with Braeburn was to look at the internal quality of the core flush. And we had apples that were showing stress, which was the one called BP CO2 stress, versus those that are high quality and no internal damage. And we're able to distinguish the two different quality attributes of fruit using this technology. I mean, it certainly needs some more work doing on it, but we believe that this could be a really good technology for internal discrimination of both fruits, apples and other fruits and vegetables. The last slide, couple of slides I'm going to talk about are the use of the University of Kent. This is looking at the surface structure of fruit. So this is looking using another technology called optical coherence tomography, where we are able to use a laser to scan across the fruit surface, and it gives you be able to identify changes in wax structure and also skin thickness. So this has been the case we're using blueberries, but it is equally applicable to tree fruit. This is the University of Department of Applied Optics at the University of Kent. One of my PhD students, Maria Carcoma. And so the technology, you can actually see the results are very powerful. So in this case, you can see as you scan from left to right, changes in the skin and wax surface of blueberries over time, and the increase in cracks and the breaking up of the wax surface. So we can also measure the skin thickness too. So has a huge potential for interrogating fruit quality over time, potentially looking at changes in skin thickness, which might impact on, say, things like CO2 injury on the fruit surface, and other sort of necrotic lesions that might occur. So just to finish off, I'd like to thank lots of collaborators in this project. So CDT, University of Manchester, NIABMR, and colleagues at University of Greenwich. Thank you.
Thank you so much, Richard. We're going to move on quickly because we are running a little bit late at the moment. So if anybody has any questions for Richard, feel free to post them in the chat room. Richard, if you stay with us, and perhaps you can look at those and answer them through that. But we must move on because we've still got 3 talks to do before lunch. Apple nectar, apple canker, Neonectia dittissima continues to be a massive problem for the industry. We've been doing a huge amount of research on this over a great number of years now. We now have Xiangming Zhu to talk to us a little bit about the work that he's been doing, and he's looking at the role of endophytes in affecting apple canker. Good morning, Xiangming. Are you with us?
Yeah, with you. I'm trying to share screen now.
Thank you. We can see you fine. We can hear you fine. And now we can see your screen. Perfect.
Okay, can you see my screen? That's good. Yeah,
we can. If you want to put it on presentation mode, that would be helpful.
It's in presentation mode. I'll try again. That's interesting.
Okay.
Can you see it?
Yeah, we can. I think let's go with what we've got. We can see it. Let's move on because we're short of time. Thank you, Xiangming. Yeah.
Okay. Just before I talk about the canker, just a quick question about the ARD. As Chris said, this is the final year of Chris, but we also have a European project looking at which is precise what Chris said. We combine the rootstock mutation and with planting in the alleyway plus the beneficial organism. So hopefully we can have more results to tell you next year about that's the strategy, whether that is effective or not against the replant disease. So talk about endophytes. So this is the this is the PBSRC funding project. Just finished next month. The efforts with the whole the pathology team includes those pathology team like Rob Saville, and he just gave a talk about GKM. And so the first thing is why endophytes. Okay, so endophytes it's essentially it's a bacteria or fungus who lives in the plant tissue for whole part of its life or only part of its life cycle. But the key thing is that without causing any apparent disease symptom on the plant. And most recently, last decades really, there are so many reports about specific endophytes can actually improve plant tolerance to pest disease, increase plant tolerance to abiotic stress such as drought stuff, and also in a couple of the perennial tree crop species, they also show specific endophyte can actually improve the vegetable propagation in nurseries. And 5 years ago, we had data to suggest the actual resistant variety to canker appears to have few specific endophytes much more abundant than successful one. That's why we wrote a BBSRC proposal with industry support. You can see from the slide, you can see from AHTB, Frank Matthews, TNG, Engine Strips, and Worldwide Food and Avalon all support this project. And this project is a very complicated project and about 6 or 7 objectives. But here I'll only talk about one. It's the dynamics of how endophytes change over time. Then my colleague Matt will talk about biocontrol after me. Why the dynamics endophytes is very important in the sense if we need to understand the turnover of the species composition in the endophytes for one reason only. If we find that one particular endophyte is really important for increasing canker resistance, then we try to artificially increase that abundance of that endophyte in the tree. The question we ask, if we actually artificially apply the endophytes in a particular time, can they persist over time, or do we need to apply annually or even more frequently within a given season? That's essentially the whole idea about looking at dynamics. Okay? So in this project, we look at the site effect on the endophyte and also the local area within a site and assigned cultivars. We have 7 cultivars and divided 2 groups. So one group is resistant to canker or say tolerant, not resistant as such, and susceptible to canker. Then we have 2 rootstocks. One is supposed to be more tolerant to canker, the other one's not. And then we have a sampling time, some 3 times in the autumn in year 1 and spring or year 2, then autumn in spring in year 2. So we have 2 autumn time in sandwich between the 2, it's a spring sampling. We sample the leaf scar tissues for endophyte because we believe in the UK condition, leaf scar is still the most important entry point for canker. Then we use the empty sequence technology to sequence all the particular region of the microbe in the leaf scar tissue, then identify them into taxonomy groups and look at the actual dynamics of time. And the first thing is really interesting is, as you say, we look at, I told you, we look at the endophyte at 3 time points, 2 autumns, 1 spring. And then we all, in addition to look at sequence data, we also look at the total biomass represented by qPCR data set. It's very interesting. You look at the figure on the left figure, there is a huge population crash of fungi from this autumn to spring, then increase to this autumn again. The scale is on log scale, so essentially it's the difference about 2 magnitude difference, a huge crash. Although the crash in bacteria is still statistically significant, but far less than fungi. So that's first really interesting point. That really implies either bacteria is really more moving, colonize the new tissue from the tree, other tree parts, or they are really fast colonizer from the surrounding condition. Okay, but fungi definitely tend to be more locally recruited during the season rather than from the original tree itself. This suggests, and also another point is really interesting on right-hand graph, was not as apparent as but you can see clearly the actual will show the statistical significance association between higher fungi population in spring leaf scar is associated with the canker resistance. That really means if you have a high fungal population or endophytes in the leaf scar in the early spring or in this early summer, it tends maybe the fungi will be able to compete with nectar entry infection in autumn. So that's an interesting point. Okay. Next point, to further support about the fungi, fungus more likely new fungal population turnover much higher than bacteria, is looking at the indication of the new species present in spring or in autumn or in second autumn compared with bacteria. If you look at the actual the graph called D fungi on the spring part, the yellow part, you have more than 1,000 taxonomy groups are unique to the spring samples. Okay, unique to spring. Somehow they lost those 1,000. The taxonomy group lost in autumn. That really meant those are essentially mean the species turnover is much higher in fungi than in bacteria. If you look at the bacteria in the spring, you have 100 of the unique private taxonomy group in the spring sample, but with the fungi, it's more than 1,000. That's a really essentially tell you same story. Essentially, is there's a far higher species turnover in fungi, indicating the leaves, the endophyte in leaf sky tissues are actually recruited more recently during the growing season. Okay, and over the last decades, people always claimed the genotypes are really most important, or one of the important factors affecting endophytes or even rhizosphere bacteria or fungi whatsoever. But here, what we showed through the multi-site and multi-time sampling, that's not the case. It's really site time most likely affecting the endophyte composition. This is further supporting the conclusion we draw, that is, it is a local recruitment of the species over time more important than anything else. So that's one of the key conclusions we draw here, and you can see this from here, the graph here, the color, the red, yellow, and blue, red, blue, and green are represent 3 sampling time point. The green essentially it's the spring sampling time. You can see for bacteria, spring sample version not different, but the 2 autumn time differ quite a lot, but most because site effect. But if you look at the actual fungi, the spring sample differs so much that really meant that the population crash from autumn to spring are randomly happening on individual trees in the same site. That's why but once over the season, the recruitment starts into the autumn, then the population structure is getting similar. That means all fungi recruitment is really happening locally in the same site. Again, and another question very interesting we look at, because there's some different in genotypes, we are asking the question, is the control of the endophyte composition genetically controlled by the apple? We found yes, to a certain extent, for some specific endophytes. You can see on this graph for bacteria and fungi, you do have significant genetic component in affecting the fungal and bacterial abundance. That really meant is potentially if one of the beneficial organism or endophyte is among those the taxonomy group affected by hosts, we can use the plant breeding technology to improve that particular endophyte abundance through the normal selection. So we are working with the breeders at the moment to further this aspect of work. Of course, one of the issues things is we look at endophytes really for canker management. Are happily to report, yes, we found certain taxonomy group, not many, few taxonomy group or actually is related to canker. For example, here you show the percentage of canopy cover which is selectively related to the canker disease is actually correct with one of the taxonomy groups. So that indicates some species or some taxonomy groups, particularly bacteria, not fungal, is related to canker resistance in particular varieties. Okay, so what we can conclude essentially say is there's much higher species turnover in endophytes, particularly for fungi. I've got around here. Should be actually fungi here, particularly fungi here, and this indicates if we want to use fungi as biocontrol to augment the endophytes, and then we do need to apply more frequently rather than hopefully they will list annually in autumn time to make sure they are established there over the initial infection period. And we are more focusing on the actually the way how can we understand the species turnover in relation to other management practice like the soil amendment and artificial application of bacteria or fungi during growing season or local conditions. That's a way we're looking to continue the work in the future. So I'll stop here. Welcome any questions. Scott, you are muted, Scott.
I'm going to ask you if you might just deal with the chat question. There's a question in the chat box, Xiangming. So if you could deal with that separately, because we must move on. Sorry, we've got a bit behind time. Yeah. So let's move on to Matt Rupar now, also of NIABMR. And Matt this is a related talk because we're still dealing with apple canker here. And Matt's going to talk us through some biological control developments for apple canker control. Good morning or good afternoon now, Matt.
Yeah, good afternoon. Can you hear me?
We can, thank you.
Oh, brilliant. Okay, let's see if this works. Did you see the slide moves? I do like a whistle stop.
We're not moving on. I don't know if you want to just try again. That's it.
Yeah, okay, so we're going to do a whistle stop quickly from a very applied angle. So we're going to look at our SEPTA+ trials from last 2 years on biocontrol, and then we're going to extend on the endophytes, what Xiangming was talking about in the last part of the talk. So the aims of SEPTA+ was very, very simple, is to identify any registered products that are already available on the market, but not registered, not yet approved for neonectria control, and test them against neonectria in lab and in the field. And we started with the 14 products. There were BCAs, so biocontrols of Bacillus trichodermas, fungicides that haven't been tested. They've been on the market for the last 4 or 5 years. And we tested some essentials or oils as well. And we just quickly run first the lab assays to come from 14 to about 8 products to have a good manageable trial in the field. And we tested if the products decreased spore germination of neonectria or mycelium growth on the plates. And then we selected the best products to go in the orchard trial, and we tested the pruning wound and leaf scar protection in the autumn and leaf fall. So very quickly, lab trial results is very variable. So interestingly, germination rate was not affected much. Here, 100% means that's how that was. What was it obtaining the water control? Is above 100%, the product is making it worse than water, and if it's below 100%, is making it better. And you can see that germination rates of the biocontrols were controlled in 2, but not in the rest. However, interestingly, the fungicides, apart from the fungicide that is at 11, which is a copper-based, there's only one that actually controlled germination. And not even, there's the standard is not shown here, but we used tebuconazole as a standard, and that didn't control germination, but it did control growth of neonectia really well. So from this, we had to choose the best 4 BCAs, 3 fungicides, and 1 essential oil that did show some sort of at least 50% reduction of at least one of our measured parameters. And we went to the orchard trial, where we then used a very high pressure disease orchard. We had run the trials on Braeburn trees that were in Braeburn Gala orchards, and Gala rows were really, really badly infected with canker, so they served as a disease inoculum. Plus, we used our own inoculation methods on top of that, and we tested. We spray the trees with a knapsack between 2 to 4 times, and then we tested whether we can protect pruning wounds, leaf scars that we infect, and leaf scars that were naturally infected. So when we looked at the pruning wounds here, we can see you have water and standard, which is tebuconazole at the number 15 and 16. You see there's no significant differences. So pruning wounds prove very difficult to protect, and maybe fungicides at the number 7 was the one that reduced the most, but still not significant. And the biocontrol really didn't come very close to effective control. Interestingly, the standard tebuconazole wasn't very good either. So that's the problem with the pruning wounds. When we looked at the leaf scars that were inoculated by us 24 hours before product application, then we see the fungicide number 6, quite good, significant, and the standard, tebuconazole, significant reduction of neonectia incidence, while the rest of the products weren't really that good. Most of them did reduce by about 50%, to be completely honest, but not, it was very variable results, so they weren't significant. 1 BCA came close, and the essential oil was remarkably good as well. So that's BCA under number 3 and essential oil number 12. But then when we looked at the naturally infected leaf scars, so the leaf scars that got infected at any point after spraying, during and after spraying, then again, we see that there was no significant differences, and actually 2 of the biocontrol seems to be making things slightly, I have to repeat here, not significantly worse, but there was slightly more cankers on when biocontrol 1 and 3 were applied. So here we can conclude that one product, the product number 6, when we applied it twice, this is a new fungicide, was quite good at protecting leaf scars during the leaf fall, but maybe less so pruning wounds or the leaf scars after they've been infected or after its application. So it has a very short period of action. And then 2 other fungicide products and the surfactant or the essential oil product 12 showed some promise, and they could probably be applied together as a combination to improve on their effect as a single. But the current biocontrols were not really effective. And I think we need to do a bit more research on the timing and number of BCA sprays. If that is cost effective and efficacious, we don't know, but we definitely need better and new biocontrol organisms to step in. With this, I'm going to quickly run through the endophyte part of the project or the new biocontrol with endophytes part of the project that Xiangming was talking about. So the endophytes are all the different organisms that are within the plants and have, they enter through various routes and have different functions from growth promotion to stress tolerance. So our question was, can we find an apple endophyte that will help suppress canker or help prevent canker incursion in the tree through wounds, so it would be there before the neonectia to prevent its entry? And we found such endophyte by looking at the differences between endophyte communities in Golden Delicious and Grenadier versus Gala and Braeburn, so resistant versus susceptible. We found this epicoccum that was called, I just put here both, but it's called Epicoccum nigrum or Epicoccum purpurescens. Is the same thing, it's just different literature where we use different names. We isolated from the site, from our own trees on the site, and we showed that it worked really well in the lab. But as we learned from the previous slides, what works in the lab doesn't necessarily work in the field. So we tested this in field conditions, and then really importantly, we tested that it does, if it causes any harm to the plant. So it could be a latent pathogen, could have other problems as an endophyte. So we tested that as well. So when we looked at the canker incidence, we did it on this 48 Gala trees that was first inoculated. The leaf scars, fresh leaf scars at leaf fall were first inoculated with Epicoccum spores, and then within a couple of hours with a really high load of Nectia spores, so simulating really high pressure. And we saw a huge decrease, about 50% of canker incidence here in green. In green square, you have when you inoculate with neonectia, about 63 to 65% of leaf scars get infected. When you put Epicoccum before on, you get 50% reduction to about 30%. And we saw a slight, only by 7%, but significant reduction of Epicoccum working even on the pruning wounds, which is really, really, really encouraging, because even some of the fungicides applied directly to pruning wound didn't work really well. What was kind of strange, but maybe expected, is that canker size itself, so how big the canker gets after infection, was not really significantly affected by our Epicoccum isolate, this B14-1. And that is probably because it can prevent intrusion, or it prevents neonectia entering the tree. But when the nectar is in, it can't really control it anymore. So that's why we kind of conclude that it's prevent entry, but maybe not then control it forever in the tree afterwards. So the second important for the biocontrol is if it does cause any harm, and we measured that by inoculating rootstocks and measuring growth and measuring symptoms on M9 rootstocks. So we saw that there was no penalty on growth, no leaf symptoms. And when we applied water or our B14-1 Epicoccum straight on the leaf scars at leaf fall, and then the next year we came back to measure how many of those the buds next to the leaf scars were healthy, we saw there was no significant differences between water and our treatment. So it means that it doesn't, even if it does colonize the tree, it doesn't cause any bud death or any other abnormal symptoms. We also tested whether we get symptoms on mature fruit, which is probably the most important thing. There was reports that some epicoccums can cause disease in the fruit, although when I checked them, it turned out that when you cut a hole in the fruit and chuck a whole load of epicoccum in, it will grow. It doesn't mean that it will cause disease. And we've sprayed mature fruit of Gala, Jazz, and Braeburn when we inoculate with spray with epicoccum spores, whether we pierced the skin before or not, and we couldn't see any symptoms, but we're repeating that just in case the second time around. And we are incubating at room temperature, and we can't see really any problems with epicoccum. So I think these are really encouraging results. And we did show that we can colonize as well in the long term, not really well, even though it was isolated as an endophyte. When we spray it on trees, you kind of increase the endophytic population, so the population in leaf scars, by about twofold, which is not really significant here. And if you put them straight under the leaf scars, epicoccum really colonizes leaf scar only, and a little bit 3 to 5 millimeters spread into the wood in the same year. But when we come and have a look at the next season, which is the point that Xiangming was making, we can't find epicoccum in the leaf scars that we inoculated in the previous season, only within the same sort of leaf fall period of the inoculation year. So it's not going to be, as Xiangming said, it's not going to be a biocontrol that's you're going to apply once and it's going to colonize the tree and protect it forever. It's going to be reapplication every year, and maybe it will have to be reapplied in the spring, where this population crash has been evident from what we've seen otherwise, and then will help Epicoccum to colonize. That's something that we need to test in the future. So quickly to conclusions. So we found one very effective and a few potential candidates for the very, very near term with some emus. You can see those products maybe in this leaf fall area and this season. But in the long term, the fungal endophyte, the Epicoccum nigrum, is a potential good candidate that might come online in a couple of years. But what I want to stress here, and this is really the most important point from this talk, is that none of the currently available spray applications anywhere in the world, not just in the UK, which in fact we have the lowest amount of products available, but even in a place like New Zealand, when they have more, there is no spray application that's sufficient for control of apple canker. So monitoring and pruning out cankers, especially in young orchards and from the top of the trees where the canker can spread with rain down, extra vigilance in young orchards where the whole tree can get killed, or the whole upper, like the production part of the tree can get killed by one little canker, and removing that out is really important to reduce your inoculum. And then the second really important is no post-harvest foliar nitrogen application. That really makes canker much, much worse. And with that 4 steps, you could probably reduce canker by about third or even 50% year on year if you do that very, very strictly. And then new biocontrol could come into that. Okay, exactly 50 minutes. So no questions, apologies.
Thank you. I've just got a very quick one that everybody will be asking. Who needs to drive this forward for Epicoccum nigrum if it's going to become a commercial reality?
So I think we need to find a good partner that's interested. We need to publish first, so people can see that this is really effective, which is on my agenda this afternoon, to be completely honest. And then we can proceed with finding a industry partner that's going to push this over the line, really.
Okay, Matt, thank you very much indeed. We must move on. Thank you to Matt. And we're moving to our final talk this morning. Sorry, we're running 10 minutes late, but I'd like to introduce Mojgan Rabier from the University of Birmingham. We've been talking about apple canker, which is caused by a fungal organism, Nondestructive Technology. We're going to move to cherry canker now, which is a bacterial pathogen, Pseudomonas syringae, and there are various pathivars. Mojgan, tell us all about the research that you're doing at the University of Birmingham.
Hello, good afternoon. Hopefully you can all hear me all right, and you can see my slide.
Yes, all fine. Thank you.
Perfect, thank you. So yes, so today I'm going to talk about understanding cherry canker bacterial population diversity and pathogenicity. So it's a BBSRC funded project in collaboration between NIAB and University of Birmingham. And so let me just briefly introduce the bacterial canker of cherries. So it is caused by Pseudomonas syringae pathovar. So it's a major disease of prunus species, including cherry, plum, peach, apricot, and other stone fruits. So it is caused by pathovars of Pseudomonas syringae species complex, including Pseudomonas syringae pathovar syringae and Pseudomonas syringae pathovar morosporinorum, that there are 2 races that cause this disease. So this disease is a globally important plant pathogen. So it infects a wide range of important crops, over 180 different plant species. So it can cause huge economic loss, and in cherry it can cause up to 75% loss of trees. So this graph here shows you, or diagram shows you, the life cycle of Pseudomonas syringae. So as you can see, it's able to infect throughout the year. So the pathogen invades woody tissues in winter and can colonize in cambial tissues and causing canker in the spring. And during the growing period, we can see the bacteria can interleaves, causing brown or black spot that cause the spot that drop out to reduce short hole symptoms and also cause necrotic lesion on fruits. And the infected trees will produce a huge amount of gummy oats, as you can see in the picture, and the tree eventually will die back. So it is an annual problem, and it is a very important disease that causes a lot of damage in the UK. So how we can stop this bacterial disease? So chemical control currently for this disease is limited to copper-based compound. So it is a treatment that has been restricted because of the adverse environmental effects and also because it's not highly effective. Also, breeding for resistance is a desirable alternative method of control, but progress has been hampered by the complex nature of the disease and because there are 3 different pathogens causing this disease and because Pseudomonas stringi is a complex species. So preventing that via this is quite difficult. So it is important more than ever to understand the population dynamic, the diversity and pathogenicity of Pseudomonas stringi, and so that we can come up with a way that we can understand the disease first, and then we can come up with the idea to control the disease. So what we already know about this disease, that we know that there are regional variation in Pseudomonas stringi population across cherry cultivars and also wild cherries. And also we know that there is significant variation in resistance to canker between the cultivars and wild cherries. Also, we know that there are epiphytic population of Pseudomonas stringi. The epiphytic are those that live on the surface of the non-diseased cherry leaves. But these epiphytes that they don't cause any damage, they might have some genes in their genome that predicted to have a key role in post pathogenicity to Pseudomonas species. So we are interested to know if this epiphytic population that live on the surface of the non-diseased cherry leaves, they are able to cause any disease and how they are able to do that. So what we don't know, and we are trying to understand during this project, is how Pseudomonas stringi population change and influenced by the environment and also by its host. As I said, this pathogen has a wide range of hosts. So could all the hosts that they are in a nearby location have similar Pseudomonas stringi population and pathovars? And for example, if you have wild cherries and cultivated ones, can they have the same and similar population? Could agronomic practice impact Pseudomonas stringi population? For example, nitrogen application, or if they are cultivated cherries, if they are covered in or not covered. Also, we are interested to know how non-pathogenic epiphytic strain become pathogenic, what changes in the genome that cause this. Do the epiphytic population have pathogenic potential? So previous research that we did found that there were some genes in the genome of the bacterial population of Pseudomonas that appeared to be gained during the coevolution, or some of the genes that were important in pathogenicity lost. So how this gain and loss in the genome affects pathogenicity. So we are conducting a multi-year, multi-location sampling of epiphytic and pathogenic population of Pseudomonas stringi. So we have 2 sampling seasons per year. So it happens in May and September. We have chosen 4 regions in the UK, so Scotland, Midland, Southeast, and Southwest. Per each region, we have 3 orchards and 2 woodlands. And from each orchards, we take samples from 3 different cultivars, and from each cultivars, we are doing 6 trees. So we're taking leaf and shoot samples. Also, from the woodlands, we have 2 woodlands per region, and we are taking samples from 6 different species that we know that they are host to Pseudomonas stringy. So we have wild cherry plum, we have blackthorn, hawthorn, wild strawberries, and also ash trees. So we take samples from all. So as you can see, this is we take huge number of samples. So then after we take the samples, we take them to the lab, and we wash the samples in the special buffer, and then we place them on agar plates that are supplemented with antibiotics. And then so far we have been able to collect 3,000 strains of Pseudomonas stringy that they are from sampling in May 2021 and September 2021. So more isolates will be collected during this year and next year sampling. So and then after we take this, after we isolate the samples from different geographical locations and from different environments, so we are then going to DNA extract them. And what we're going to do, we're going to then genome sequence them to see what's the difference in their genome. And also what we're going to do, we're going to also test the pathogenicity on cherry leaves and cherry shoot and bark. And then so these data will provide lots of different information about the pathogenicity and the population of Pseudomonas stringy on cherry leaves and their surrounding host species. So this is being done in NIAB by Dr. Tracy Ring. So also another important factor is to see how epiphytic non-pathogenic population become pathogenic. So we want to understand if the gene exchange between bacteria can be mediated by bacteriophage. So bacteriophages are viruses that infect and kill bacteria. We can use them as biocontrol agent to control diseases. However, sometimes when bacteriophages infect bacterial population, they can incorporate and integrate their genetic material and their genome inside bacterial genome. So then we call them prophage. However, these prophages that now they, as you can see in the top graph, that are called Pseudomonas stringy pathovarmor sporonorum. So you can see there's already a prophage inside the bacterial genome. So then this prophage, when integrated this genome inside bacterial genome, can sometimes become activated and can leave bacterial genome again under some stressful conditions, for example, under high UV light or high temperature. And then as it leaves the genome of bacteria, it can take some of the genes that are inside bacterial genome with it and take it to another bacteria. So whether it's a virulence gene or is it not a virulence gene. So if when it leaves the genome, take a virulence gene with it, it then can transfer that gene to another bacteria. So can it occur in the cherry leaves environment? We are trying to understand that. So we know that there is a virulence gene that is found within a prophage in Pseudomonas stringy pathovarmor sporonorum. That using bioinformatic tools that we know there is a high probability that it can become active. So can it then excise and leave the genome, and can it move the virulence genes to another bacterium? We are investigating that. So we will be able to understand what triggers the phage to become active and how it moves around and how it can move the virulence genes around. For example, if the strain receiving this virulence gene is the epiphytic non-pathogen, by receiving the gene, can it become pathogenic? So what this research means to cherry growers, so with practical knowledge about how crop nutrition and crop covering affect disease, we then are able to change our practice, agronomic practice. Also data on pathogenic and epiphytic population of Pseudomonas stringy, its potential pathogenicity, and there are the other host and wild relative which could inform our future biocontrol of this disease. Also understanding how similar Pseudomonas stringy strains are on different hosts, how easy to host jump onto related hosts will have impact for disease management, for example, choice of hosts to plant, for example, which host you can plant around cherry trees that they maybe it will not host the pathogen. Also understanding the risk of epiphyte that pose if they become pathogenic will help us to develop precision diagnostic of for prognosis species as well as in other crops, and establishing if bacteriophages are actively transferring virulence genes within bacterial population has implication in the use of this microorganism as biocontrol agent in terms of ensuring there is no genome integration in the cherry leaf environment. So thank you all for listening, and I'm happy to answer any questions.
Thank you, Mojgan. It's very clear, and we don't appear to have any questions, but my question to you is, how much longer would the phage work go on for?
So for another 2 years, so 1 year away has been gone, and we did lots of sampling, and hopefully within this year, we are going to publish a paper on the how prophages and phages can move genes around. So keep an eye out for this publication. And there are 2 more years to go do more research on this.
Okay, well, perhaps you and I can keep in touch over this, and I can do what I can to try and disseminate the results of your good work to the industry, because people will be very interested to keep an eye on this. So Mojgan, thank you, and thank you to all our speakers this morning. We're going to have a break for 45 minutes. If anybody is leaving us at this point, you may well be prompted to fill out a form questioning you on the success of today's event and how much you value it. So please do take time to complete that. Can I remind anybody, if you want us to apply for basis points on your behalf, please send me your details to my email address, scott.raffle@niab.com. So we're going to take a break for lunch. Please stay with us. Our second session starts at 1:35 sharp, and we will be focusing in our second session on advances in spotted wing Drosophila control. Our final session then will focus on other IPM techniques for pest control in tree fruit. That starts at 3:15. But for now, please enjoy your lunch and do join us again at 1:35.